Okay, so this will be part A of the lecture for water. We'll deal with running water in this one. So basically streams and rivers. So what we're going to be talking about is part of the hydrologic cycle. The hydrologic cycle is the circulation of water within the Earth's environment. The parts of it that we're going to be looking at, of course, if we start out with a landscape like this, we have an ocean, we have a mountain off to the side here, just out of reach. We get evaporation, converting water into water vapor. Then we get condensation, which is going to create clouds. As the clouds move inland, they can be forced upwards by the land in what we call an orogenic effect, or orographic effect, I should say, and that can cause precipitation. When you have precipitation, you're going to get water hitting the ground. One of two things is going to happen. You're either going to get runoff or infiltration. The infiltration is going to head to the groundwater system, and that's going to be part B of this lecture. Part A is going to be dealing with the runoff. Now that runoff can also then, when it encounters vegetation, the vegetation takes up some of the water, and it undergoes what's called transpiration or evapotranspiration. This would be like if you've ever taken a hike down to the Santa Cruz River during the summer. You notice that you say you start in downtown, in the Old Town Tubac area, how warm it is, and by the time you get to the river, how much cooler it is. And it's because of not only the shade from the trees, but the trees are giving off water as they're respirating, and that water is evaporating, and that evaporation is causing a cooling of the temperatures. Now, generally speaking, the water cycle is balanced. The water system is pretty much balanced. Yes, there's a little bit of loss here, a little bit of gain there, but over short-term human time scales, it's negligible. So how do we start with getting water that's moving? Well, we start with the water hitting the ground, okay? And that's going to cause what doesn't soak in is infiltration is going to start to run off as what we call sheet flow. This is basically, just imagine it's a very thin sheet of water that is moving across the surface. Now, how much water is that going to be? Well, that depends on a number of factors. Generally speaking, the natural desert around us or natural steplands around us, that's going to be roughly 70% of the water soaks into the ground, 30% runs off. But go to the Walmart parking lot, 95 to 99% of the water that hits the ground runs off. So how much water makes it into the ground is going to be controlled by 4 different factors. One is how intense and how long does the rainfall last. A rainstorm that drops 1 inch in 20 minutes is going to produce a lot more runoff than a storm that dumps 1 inch over 24 hours. So the faster the water's coming down, the harder it is for the ground to absorb it. Do we have prior wetted conditions? In other words, is it already wet? We see this during the monsoons here in Santa Cruz County or in Arizona in general, where you can have one storm that hits an area and then it's followed up the same day by another storm. Generally speaking, even if they are exactly the same storm event in terms of the amount of rainfall that they produce, or even if the second one is slightly lesser in terms of the rainfall that it produces, it will produce more runoff because the ground is already in a prior wetted condition, meaning that it's already absorbed some of the water that it can absorb. And if you're throwing more water on top of it, it can't absorb anymore. It's like taking a wet paper towel and trying to get it to absorb more water. It's hard to do. Of course, there's also the slope of the land. The flatter the slope of the land, the slower the runoff is going to be. Therefore, the less runoff you're going to see. The steeper the land, the more runoff you'll see. And then the nature of the vegetative cover. Vegetation does a wonderful job at not only slowing down water, if it's a dense vegetation like a grass, especially a knitted grass or a carpet grass, versus, say, just individual standing trees. While the canopy will intercept a lot of water, the ground itself tends to be barer underneath and not able to absorb as much water. Now, this water as a sheet is going to work its way across the landscape, and ultimately it will start to collect into rivulets, little channels. Once it does, then it's going to begin to flow downstream. Now, how the flow behaves can be based in part on its velocity. Generally speaking, there's two types of flow in water. Excuse me. One is called laminar flow. Laminar flow is where all the water is moving in the same plane at the same time. It's not mixing vertically or at all. It's all moving in the same general direction. Maybe you've seen water fountains where you have water being sent up in arches, and that arch of water hits the water pool and it doesn't splash, doesn't seem to cause much of any splash. That's usually called laminar flow, and it holds its shape for that entire distance. It takes a lot of work for us to artificially make laminar flow. The other is turbulent flow. Turbulent flow is where the water molecules are moving in all different directions at once. Generally speaking, it's all going downstream, but at any one time, some of it's moving up, some of it's moving down, some of it may be moving backwards. And this helps mix things. And this is one of the things that's, one of the ways you can tell this is usually you see currents of water bubbling up and bringing up mud and a lot of silt. Very muddy, very silty water tends to be very turbulent water. Now, in terms of how fast does the water go, or how do we determine the velocity, basically the factors on that are fairly simple. One is the slope. Obviously, the steeper the slope, the faster something can move. Just think about it as you're driving a car. If you're on a very gentle slope, take your foot off the brake, let the car run by itself, it might pick up a little speed. Get on a 6% slope, a little bit steeper, although not all that steep compared to a real angle, but your car will pick up the speed a lot faster and will go a lot faster. And then there's the characteristics of the channel. The size of the channel matters. A larger channel can obviously hold more water and can allow that water to move faster, but that's going to also be dependent on the shape of the channel. It turns out that the most efficient shape is going to be a semicircular channel. And this is gets down, you can get into the mathematics on it where you're looking at the surface versus the wetted perimeter, and that has the lowest ratio for that. Or the largest ratio, I should say, for that. The larger the ratio of the surface length divided by the wetted perimeter, the slower the water is going to tend to move. So you want a smaller ratio, closer to 1 as possible. And a semicircular channel does that, which means the water is going to be the fastest in the center of that channel. And it feels, you have edge effects, so it feels what's happening at the edges. Which brings us to the idea of roughness. How rough is the channel? Are we dealing with a channel that's made up of cobbles and boulders, or are we dealing with a channel that's all very fine-grained silt? A fine-grained silt channel is much smoother than a cobble channel. So this has to deal with how much water, how the characteristics of that channel are going to affect that flow of water. And then, of course, the final determinator is the discharge. How much water is being moved per second. Now, in terms of units, we use cubic feet per second as discharge in the United States. Kind of hard for a lot of people to initially get a grasp on what's a cubic foot. Well, cubic foot is 7.489 something gallons. Well, I'll call it 7.5 gallons. Still, that's kind of hard to, 7.5 jugs of milk per second. That's kind of hard to visualize. Better one for you. A basketball. A basketball is about 1 cubic foot in volume. So when I say cubic feet, you can imagine basketballs of water. So the Santa Cruz River, for example, near Nogales is about 35,000 cubic feet of water per second during its peak discharge. The Nogales Wash in Nogales is ranges between 14 and 19,000 cubic feet per second. Now, the interesting thing is that as the discharge goes up, the velocity will go up also, depending on a formula where Q, which is the discharge, equals VA, where A is the cross-sectional area of the flow and V is the velocity of the flow. So you can see how they interrelate if you change one and what the effects are on the other. So if you hold the velocities constant, you increase the discharge, the area of flow has to increase. And if you decrease the discharge, the area of the flow has to decrease. Whereas if the area of the flow has to stay the same, then the velocity has to change. Now, there are some changes that occur in the stream. Now, generally speaking, when we look at a river system, it does have a shape to it, if you will. It's a relationship of elevation to distance. And I'm just going to sketch it out here, but generally speaking, it looks something like this, where this is going to be distance down here, and this is going to be elevation here. Okay, so this distance, this point right here is going to be the mouth of the system. So it's where it's discharging. This could be into another river, it could be into a lake, or into an ocean. Generally speaking, this leads us to an idea of what's called base level. Base level is the lowest point that a river system can cut down to. Ultimate base level is going to be whatever the current sea level is. Now keep in mind, sea level will change. During the height of the last ice age, sea level was anywhere between 200 and 400 feet lower than it is today. So the fact that sea level can change means that base levels can change. But in terms of human time scales, sea level doesn't really change that much or that dramatically. At least not that we've seen yet. So some of the things that we'll see is, one, the further back we go up this way, one of the things that we see is that as we go this way, velocity increases. So velocity will increase in the system the further away we get. And that's in part due to the fact that the general slope of the system is going to increase the further back we go, the further upstream. However, the discharge increases in the opposite direction. And this is because the area that is contributing water, or the watershed, is increasing as we go downstream. We'll talk about that more in just a moment. We also see that channel size, so channel area, tends to increase as we go downstream, which makes sense. We're dealing with more water, therefore bigger channels. Let's see, some other things that will happen. A couple of interesting things. Let's talk about the amount of material the river is moving. Okay, that's going to be the sediment load. And we'll talk about different types of sediment load here in just a minute. But the total load increases as we go downstream. But the competency increases when we go upstream. Now, what do I mean by competency? Well, competency is a measure of the largest particle that a river system or stream system can move. A good rule of thumb for simplicity for our level at this point is that look at the bed of the channel. The largest particles that you see in the channel tend to be the largest particles that that system can move at some point during its run, whether that's a flood stage or its normal run. Generally speaking, if it's a normal run, if it's a clear running system, you can actually see the particles it's moving and get a measurement for them. And then anything that's larger than that, it's not moving right now. If the stream is moving perfectly, totally, and utterly clear, no sediment moving, then it's moved everything it can move. The material is armored until there's a disturbance, and then it can pick up more material. The competency is the largest particle it can move. So this gets back to velocity, which is related to energy of the system. So obviously, the more energy the water has, the larger the particle it can move. Generally speaking, when we look at it, also what we see when we look upstream is the roughness, which is sometimes called the N number, increases as we go upstream. So the channel gets rougher the further upstream we go. The slope gets steeper, and so forth. So you can see how those reactions change. Now, interestingly enough, we can mess with this. If we come in here and put a dam in here, we're going to artificially change the base level, and that's going to cause a change in the way the system wants to react. It's going to cause deposition near the dam. It's going to cause erosion upstream of there because the system wants to get to this curve. It really does. So it's whenever you make a change artificially in that system, the system's going to react. So another example of this is if we came in here and dig a hole, sort of like say a sand and gravel mine, kind of like they did in Tucson over 100 years ago. The system doesn't like that, and it's going to try to fill that in, and it's going to fill it in by moving that hole and stretching it upstream. Now, it's usually what we refer to as a form of a head cut. A head cut is an erosional feature in a river system that is moving upstream towards the head of the river. It can be a small drop. It can be a large drop. Technically speaking, a waterfall is a form of a head cut. Take Niagara Falls, for example. Niagara Falls is moving back upstream at a rate of a foot every few years. That is a form of a head cut. It's head cutting its way back upstream. So that's an erosional feature that we can keep in mind. Now, generally speaking, how does a river move particles? How does it do this? Well, first and foremost, it's going to be lifting particles. Now, some particles it's going to be lifting just simply because they're light enough and they're buoyant enough to be picked up. Other particles, it's abrading. You get some sort of an impact or a glancing blow that pops the particle up and allows it to move. Now, the way that sediment gets moved is dependent on the energy of the system, but regardless of the energy, we can break up that sediment into one of three types of what we call load. Load is just the term that we use for the material that's being carried. The first load that we can consider is the dissolved load. It's an easy one to consider, and it's an easy one to then forget about for now. The dissolved load is going to be anything that can be dissolved in water. So obviously, it's not a physical particle anymore once it's dissolved in the water. So we really don't have to worry too much about it because it's not going to get redeposited until the water evaporates. The second one is the suspended load. This is the material that's going to stay in suspension. In fact, actually, I can demonstrate that. With a jar of water and sediment. Okay. Now, if I shake this up, stir this up, I got to get it broken up because I have not done this in a while. There we go. You can see that as I'm shaking and stirring, I've got material in motion, okay? Now, this material is currently suspended. And when I stop, you can kind of see it. Some of the material is settling out. And we have material that is still in suspension. It's held in suspension for now until gravity comes out. I will set this down over here. I'll try to remember to come back to it. But suspended load is basically material that is being carried by the turbulence of the water, being kept up in the water column, usually by turbulence. The third load is the bed load. The bed load is the material that is moving along the bottom of the channel. Now, this material, typically speaking, is going to be like rolling material, but it can also undergo a different form of motion called saltation. What saltation is imagine I have a little pebble and it's rolling along the surface and there's a bigger rock sticking up out of the bed of the channel. When that hits, it pops up, and it takes a trajectory something like that. And when it hits again, it sends material up, and then it keeps rolling on until it finds another obstacle. That's the form of saltation. If you've ever been outside during a sandstorm or a dust devil wearing a pair of shorts or a skirt or a kilt or whatever you decide to wear, and you felt the little pebbles and sand grains hitting your legs and your thighs, that's a form of saltation. It happens in the air as well as in the water. But that's the way the material is moving. So it's either rolling or it's going through this bouncing motion, which we call saltation. And again, we get to capacity. Capacity is the total amount of sediment that the system is carrying. Again, the further downstream we go, the greater the capacity becomes. And that simply is because there's more water. So that increases the amounts, especially in suspended and dissolved load. But competence is the maximum particle size. And it's again determined by velocity. Now, velocity also is important not only for moving the particles, but in how the particles get deposited. Deposition in a river system occurs whenever water slows down. Let me repeat that. Deposition occurs when water slows down. So anytime we are slowing the water down, we are causing deposition. So a good rule of thumb is where water, all else remaining equal, when water picks up speed, it tends to be erosive. When water slows down, it's depositional. Okay? So when we decrease the velocity, we decrease not only the competence, but also to some degree the capacity. So we're going to cause sediment to drop out. This tends to create what we call alluvium, which is stream sediments that are usually well sorted. Not always, but they usually are. We get different types of deposits depending on where this deposition is occurring. We can have deposition within the channel, in which case we can see braided streams. These are streams that run into and out of each other. Very common down here, actually. Also very common in glacial environments. So a braided stream is literally where you have multiple channels that are all intersecting and running in and out of each other, kind of creating like a braided mess. Okay, that would be a braided stream system. Usually, this is very indicative of a system where the streams are carrying more sediment than their limit, pretty much. So they're dropping sediment at the same time they're trying to pick up sediment. So they're pretty much at their sedimentary limits in terms of their capacity. So again, we see this in glacial environments, meltwater coming out of glaciers carrying a lot of material. We can also see this in areas where you have a sudden, very drastic change in the slope of a stream channel, such as what we see here when the streams come out of the mountains and they hit the valley floor, the Santa Cruz River Valley, that they create delta deposits that we call alluvial fans. And usually what you'll see on the distal ends of these alluvial fans are braided stream networks. Let's see. We also have deltas, which are basically where the sediment is being dropped because of a sudden decrease in velocity. When we look at rivers going into an ocean or a lake, that's where we tend to see our delta deposits. Delta deposits have a very characteristic form to them when you look at them in cross-sectional, and it's the way they're laid down. So there are three types of bed sets in a delta deposit. So the first set we tend to see are these horizontal layers that we call the bottom set beds. Okay. This tends to have on top of it a form of cross-bedding, which are called the foreset beds. And then on top of the foreset beds, is another layer of horizontal layers we call the top set. This is, you know, if you think of it this way, the water is moving in this way. The fine, super fine grain material is going out and depositing in front of it. Then material is forming this slope as the delta is moving forward. It's being built up as a slope, and then you have the layers on top coming in. So very characteristic. If you see this sort of depositional characteristic, you know you're dealing with an ancient delta deposit. Strangely enough, out in the Canelo Hills area, it was a deposit like this where they found tyrannosaur teeth. So out near Sonoyta. Now, generally speaking, we can also have floodplain deposits. Floodplain deposits are going to contain things like a natural levee. This is when the water comes out of the channel, especially during a flood event. The water is going to tend to be fastest within the channel, and as it goes out onto the floodplain, which is the flat area of land associated with the channel, that water is going to be losing the most energy right as it's leaving the channel. So it's going to deposit a lot of sediment right there, creating a little mound that runs along the channel, a natural levee. And it's built up by successive floods. Now, in the floodplain itself, we can get graded bedding deposits from a flood. So again, those are those deposits where the material at the bottom of the layer is coarser and it becomes finer as we go up to the top of the layer. We can also get back swamps, which are caused by water trying to get to the river, but being blocked by the natural levee. And we can also get what are called Yazoo tributaries. These are tributaries that are trying to get to the main stem of the river, but they're blocked by the natural levee, so they have to parallel the river for a distance until they're able to find a way in. Then we have alluvial fans. Alluvial fans, very, very common in more arid environments. Basically, you have a river coming out of a steep mountain canyon, hitting a flatter valley floor, and it's just dropping a bunch of sediment right there, creating a semicircular fan-shaped material. And it's interesting because it's graded, coarse material near the point where the river comes out, fine material at the end. You can also see different forms of grading within that vertically. It's actually pretty interesting to cut through those. Now, if you get a bunch of them that are overlapping alluvial fans, as we'll talk about when we talk about deserts, that's actually called a bahada. Let's see. Then we have the stream valleys. Stream valleys, generally speaking, have a very specific shape to them to start out with. And the shape of a valley actually kind of gives us an indication about how old the river system is. So let's look at that real quick. In what we would consider a young valley situation, we tend to have a strong V feature. So the channel is going to be down here. There's our water, and we have a V-shaped valley. In a middle-aged valley, we may still have a V-shaped feature, but now we got a floodplain that's associated. So the valley is widened out. And this is going to be because the channel is going to be moving back and forth through the system. Water will not run perfectly straight all the time. It will start to develop curves within it, and those curves can cause erosional forces on the sides of the valley and widen the valley out. In an old age valley, we might see something like this, where this is going to represent a break in the profile, but we have a very wide profile, very flat area with the channel in between. Now, this also means that we can see some other features in it. In a narrow valley, you're going to tend to have what are sometimes referred to as cataracts, also known as rapids and waterfalls. You're going to tend to have very large material in the bottom of the river. The medium one, you're starting to get more sand, less gravel. You're starting to see things kind of slow down. And then in the old one, it tends to be very fine-grained silts. And one of the things that we'll see is that in In this one, the river is going to tend to be fairly straight. This one, the river is probably going to meander around a little bit. The old one, river can literally do this. It's wandering all over the place. Okay. So what we have here is, if we look at a gradient also, a slope, we see that here the slope is very steep in this one, much flatter in this one, and darn near flat in this one. In fact, some segments of the Mississippi River where it's really old, near as you're getting down towards the Mississippi Delta, it takes miles to get 1 foot of elevation change. So that's part of what we can see with these systems. Now, when we look at a drainage system, we'll see, especially a well-developed one like the Mississippi River, we can see that different parts of the system are at these different stages. The old stage is definitely the lower portion of the Mississippi River. The medium stage is is further up, say near Grand Rapids, Michigan. And then if you go even further up, follow, say, the Missouri River or the Ohio River into their headwaters, that's where you get into the V-shaped valleys. And also in the wide areas, we can also, besides having the floodplains and floodplain deposits, we can get these other features that are dealing with meanders. And a meander is basically where the river channel is curving around. Now, it has a natural progression of evolution it wants to go through. So let's look at a meander. I'm just going to draw a simple one here. Okay. This is a meander. If we turn it this way, sometimes referred to as an oxbow because of the shape it takes. Now, when we look at the meander, especially if we look right here, across it, we can see a specific form to it. It looks something like that. Okay. This is a very simple cross section, but it's a very, very telling one that you're dealing with a meander, because this is what we call a meander cut. So if we look at this, this is actually the cut bank over here. This is going to be what we call the point bar. And that shape actually tells us a lot about how the water is going to be flowing. It's going to cause the water to spiral through the system. The water is going to spiral in sort of like this, as it's going, so it's spiraling through. And the reason for this is that the water wants to try to move as a cohesive single unit. So imagine a baseball bat. If you take a baseball bat and you swing a baseball bat, which part of the bat moves faster? The part in your hand or the other tip of the bat? Think about it. The tip of the bat actually moves faster. Why? Well, it's covering a greater distance in the same amount of time. Distance divided by time equals velocity. So since the end of the bat is moving farther in the same amount of time, it has to move faster. Same thing for water trying to go through a curve. The water wants to try to go through a curve as if it's a solid unit. It can't, so that creates a... Sorry about that. So anyway, we have the meander and the water is trying to move through it, and the water on the outside has to move faster than the water on the inside. This causes it to corkscrew through, creating this vertical cut on the outside, and then the water is depositing the material on the inside. So we get the meander cut and the point bar that gets left behind in the shape. Now, this is an unstable shape because if you look at it, water has one basic rule it wants to follow. It wants to go downhill as fast as possible. Well, we can look at a measure that we call sinuosity as the distance between point A and point B as measured by a bird and the distance measured along the river. Obviously, the one along the river is longer than the by the bird. So if we do the AB distance that's dotted over the AB solid distance, we get a number that is representative of the sinuosity of the river. Anything significantly above 1.4 usually is considered to be a sinuous river system or a meandering river system. So generally speaking, these things are going to be unstable. And as such, what can happen is something called an avulsion event. And that's basically going to be where suddenly this river decides, hey, you know what? I can go this way. And it cuts off the oxbow. And sometimes that oxbow can get cut off, and with a deposit that basically cuts it off completely. If the oxbow is full of water, it's called an oxbow lake. Otherwise, it's just an oxbow scar. We see this with the Mississippi River all the time. You can actually see it. You can see trees that are lining these old scars, these circular tree shapes, or semicircular tree shapes, that lines of trees that are basically outlining where the channel used to be. So that's something that we see happening with older river systems all the time. Now, we can also see these things in what we call incised meanders or incised stream terraces. Generally speaking, what we're talking about is a system where the base level for the stream has drastically altered. Generally speaking, the base level has dropped in some way, shape, or form. So what we can see this as in a terraced environment could be something like this, where maybe this is an old floodplain that's abandoned. Then we have another floodplain down here that's abandoned. Now this is the current floodplain. Kind of like the Nogales Wash and Potrero Creek. But this is where basically the system has dropped a couple of times. And this is usually by changing of the base level of the system. So basically this could be caused by either sea level drastically dropping or the river system or the land under the river moving upwards. As long as the river can cut down as fast or faster than the land is going up. We see the same thing in parts of the Grand Canyon with what's called the goosenecks. These are meander cuts, meanders that are actually incised very, very deep channels. They're over, they can be a couple of 100 feet deep, and it's incised almost vertically. That's basically because the Colorado Plateau rose up and the river cut down through it without straightening out. It's the only way it can happen, actually. The terraces are basically more like floodplains that have been abandoned as the river dropped down. Generally speaking, in those type of events, the evolution of the landscape is going to go through two processes. One is what was called a degradational state. Degradational meaning that the river is cutting downwards. Aggregational state is where the river is piling up material and growing upwards. So a degradational state, the river cuts down. It cuts down first, and then it begins to widen. This is what we're seeing along the parts of the Nogales Wash and the Potrero Creek in between Nogales and Rio Rico. It cut down, now it's beginning to widen, it's beginning to threaten homes and roads and infrastructure. So generally speaking, that is a natural process. It's one that is going to happen. We have to learn to work with it, not work against it. In terms of the drainage networks, again, the drainage basin or the watershed is the land area that contributes water to the river system. So if we draw it out, if we were to draw a network of rivers, where we can see the different branches of the river, the different tributaries. Okay, so here's a quick river system drawn out, different stream channels, part of a river system drawn out. If I take a look at the topography of this, I can draw a line around this. That line will represent a boundary. On one side of that line, any drop that falls on the ground is going to, assuming it rolls all the way through, is going to pass by a given point through that system. Otherwise, it's going to go into somewhere else. So let's just say I'm going to take an arbitrary point. I'm going to make a dot right here, right there. If I look at the topography, I can then say, well, if I had the topography, which I don't have, but let's just assume I do, this outline is the watershed or the basin. This is what is contributing water to the system. Okay, I can then do subbasins. So I can pick another point up here and have a subbasin. So any drop that falls within that area is going to pass by this point right here. Okay, so that's the watershed. Now, the boundary between watersheds is going to be called the divide. So it divides different watersheds. In North America, we have what we call the continental divide. The continental divide basically divides the continent in half, not perfectly, but in terms of on what the west side of the divide, all that water is going to make its way into the Pacific Ocean. On the east side of the divide, it's going to make its way into the Atlantic Ocean. Now, this also gets to an idea about patterns. What does that look like to you? Somebody might say a leaf, somebody might say a tree. Either would be acceptable answers. This is what we call a dendritic stream pattern. It basically looks like a tree or a leaf. You can actually tell something about the landscape from a dendritic pattern in terms of the way it's shaped. How steep is the system? For example, a very steep dendritic system might look more like this down here. So it looks like a much steeper tree or a taller, thinner tree. But that's not the only type of system that we can have. And sometimes these systems can be useful for understanding the landscape below it. One of them that's useful is the rectangular system. A rectangular stream system literally looks like it's made of straight lines and segments. Generally speaking, straight line river systems are suspect in nature. They generally mean only one thing. That is a river system that is founded within a fault or a joint system within the landscape. So it's a plane of weakness within the rock that it's taking advantage of, and hence the regular pattern of it. But it's either going to be, if you have a bunch of them together to create a rectangular system, then you're looking at probably a joint system that the river is following through, rather than a set of faults. Usually faults are going to be a one-time thing for the river. Now, another type is the trellis. The trellis river system usually occurs when you have a river that is superimposed on a mountain range as it rises up. So you end up with maybe mountain ranges that are created by anticlines and synclines, and this older river was going through, and now you have the drainage in the synclines, the anticline is in between. This would be what's called a water gap. It was cut through, but it creates a pattern that looks like a trellis work. And again, that's usually when you have that sort of a system going through. We can also have a radial system where the streams all seem to be radiating outwards from a central area, like this, or a starburst pattern maybe. Very, very reminiscent of a potential starburst or even a star. But keep in mind, in this pattern, the V's point downstream. So this area here is a high point in the center, and it's going lower outside. Obviously, the most obvious feature for this is going to be a volcano. Sometimes also referred to as a radial pattern. And then you can have a couple others. There's a chaotic pattern. You know, we can talk about those at a later length, but that one's a little more, a little less than something that we normally see anyways. Again, we've already touched on headward erosion, but we also can get what's called stream piracy. Water wants to go downhill as fast as possible. If you have one stream that is running and another stream cutting in towards it, and that cutting stream is lower, it can actually capture the headwater of the other stream in what we call stream piracy or stream capture. And we can go through now. The last topic I want to touch on this is floods and flood control. My day job. Flooding is a condition where you have more water than the system can hold. Generally speaking, it's more water than the channel can hold. In Arizona, a natural channel can only hold what is called the 2 to 10 year event. What do we mean by that? That's an event based on probability that is expected to happen every 2 years or up to every 10 years. Most large floods overflow the banks and cover the floodplain with water. We can have different types of flooding based on different conditions. There's flash flooding, much of what we see around here. We can have regional flooding, which is a little less common, but again, it's something we can see on the Santa Cruz River. Last time we saw a regional flood on the Santa Cruz River would have been 1988, and that was the result of a tropical storm that came in, parked itself pretty much near the Sonoyta area, and dumped several inches of rain over the course of a week. We can see flooding caused by ice jams. Not down here. Don't see ice on the rivers that much, but up north in the northern tier of the country, where you can have ice that freezes up, the rivers freeze up. When they start to thaw, that ice breaks up, that ice starts flowing, it comes to a constriction, the ice piles up, creates a dam, or a jam, as they call it sometimes. We can also see dam failures. For us down here, the big concern for dam failures are going to be like Peña Blanca Lake or Patagonia Lake. Not too much in the way of concern because there's not a lot of people downstream of them, but still it's a concern. Now, flood control is a realm of debate for what do we do? How much control can we really have? Keep in mind, the more we develop, the more we build homes, the more we build roads, the more we build buildings and parking lots, the more runoff we're going to have. Again, we're getting to that idea of infiltration versus runoff. All those items, roads, buildings, parking lots, they're what we call impervious surfaces. So water cannot percolate through them, the water runs off. This leads to what we call urban-caused flooding. As an area urbanizes, it causes the water to move faster, causes there to be more water, so it causes more flooding to occur. The flooding that occurs in Nogales today, on a general basis, was something that was seen only every once in a while over 100 years ago. A lot of it is due to the fact that the watershed is urbanizing, especially down in Mexico. How do we fight this? Well, there's a number of ways to do it. We can build artificial levees. Problem is that those things have to be religiously maintained. They will fail sooner or later because they're only built to hold a certain size event. Sooner or later, a bigger event happens. Therefore, you have a problem. We can build dams. Again, that's only a temporary solution at best. Again, they require a lot of maintenance, a lot of land, a lot of money. We can channelize. Channelization is something that we have done for the better part of 70 years in this country, and in a lot of places it's a failure. It lasts for a period of time, but then you've got to rebuild it. Well, but then you got to rebuild it bigger. We're kind of in that situation with the Nogales, Washington, Nogales, Arizona right now. We need a bigger channel to handle the water. When they built that channel, it handled all the water. Today, it doesn't. So we need a bigger channel. Well, to build a bigger channel, you got to take private property. Not going to make people happy doing that. You're going to have to figure out how to move the sewer line, which is not going to be cheap. And that's just to go deeper. And if you want to go sideways, well, not only is it private property, but it's roads. Hohokam and Morley Avenue potentially go away. Well, there's a problem there. And then you got the railroad in the way. You got to get rid of the railroad. So it's not an easy solution to channelize. Not to mention that if we channelize with concrete lined channels, they're not good. They actually increase water pollution. They are much more deadly than a natural channel is. They've seen this in studies in the LA River Basin. The longer a channel is concrete and you get somebody lost in the channel, and the less likely it is you're going to be rescuing somebody, the more likely you're going to be recovering somebody. And if it's a really long concrete line channel, the less likely you're recovering a body, more likely you're recovering body parts, because it will literally be a meat grinder. So we're looking at more non-structural forms of flood protection. Rainwater harvesting, infiltration galleries, even the idea of a sponge city. My son went to Singapore for a semester overseas 2 years ago. And my brother took me to Singapore to help my son move back. It was a surprise for my son. First day we're there, it was raining. Not a big factor. Singapore is like 9 degrees north of the equator, so it's in the intertropical convergence zone, so it's in part of the rain belt. It was raining about an inch an hour, and it had been raining that way for most of the morning by the time we went out. So it had been raining that way for 3 or 4 hours. Down here, if it had rained that much over that period of time, Nogales would be in the water. No doubt about it. Nogales would be underwater. The thing that amazed me is walking downtown Singapore, there was hardly any water in the street, hardly any water in the runoff channels. And that's because they've developed the city to capture rainwater. They're doing it with rooftop gardens. They've got hanging gardens off the sides of buildings. They have infiltration galleries. They have cisterns. They're capturing the water to be able to use it. I think that's something that we need to consider doing. We need to consider doing things like rain gardens and cisterns and infiltration galleries to try to better things. One of the things that we've instituted in the flood control district for Santa Cruz County, when we have a development coming in, and the development is required to do a detention basin, basically a basin that's going to capture the excess water and meter it out more slowly so it doesn't create more flooding downstream. We're now requiring those basin bottoms to be treated with rain garden techniques, because it's been shown that that can actually get more water to soak into the ground. And of course, that leads us to a discussion, which will be next time, about groundwater, which is where the vast majority of us get our drinking water from. So I will see you guys for that later on. Bye.